Hi everyone and welcome back. In this lesson we're going to be looking at the input mapping layer as part of our ongoing project example. So the input mapping layer is the first place where we bring in information from our physical system into the project. It's the only place that we bring in information from our inputs. This is digital inputs and analog inputs, as well as any inputs that would be coming over a network. So what we have here is a program which is being called by our task manager. And if we have a look at the order of the task manager, which is here, you'll see that input mapping is first. So before we do anything else in our project, we bring our inputs into their structures. So let's just run through what's happening. So before we do anything, I have a simulation switch manager or management. It's whereby I toggle a simulation status, and then I have another one here which is doing our auto feedback. We'll come on to auto feedback in a second. And on this network here, I simply reset the button requests from our HMI or SCADA system to make sure that they don't stay active for the next scan, which would then untoggle the switches that have been pressed, the buttons that have been pressed. So now we get into the actual mapping side of the system. So here we are mapping our first switch. So the switch that we're mapping here is going through a dedicated mapping layer that is solely created to handle the process data for a switch, so DUT switch, and then the simulation data for a switch. So the simulation data is DUT sim switch. And then here we have our actual I/O switch state. So this is the actual signal coming from our input layer, from our input hardware. So if we go inside and have a look, it's very, very basic. If our simulation switch is on, then we pass our simulation data I/O switch status into our process data I/O switch status. If simulation active is not on or is not true, then we come down here and we pass the actual I/O switch state into our process data I/O switch status. Now the reason we do it like this is because we can guarantee then that no matter whether we're running in Simulate or if we're running off of the real inputs, our code from this point onwards doesn't know the difference. I've seen some code and some examples in other projects where people run actual simulation code, which isn't the same as the code that runs in the actual project when you're not in this commissioning and simulated status. Now that's fine. There's nothing wrong with that if you can guarantee that they work exactly the same way. But the problem is you're not actually testing the code that you end up using. You have a different entry point into your logic. I prefer this approach because the entry point is your actual process data here. So process data, I/O switch status. And it doesn't matter where that's come from. You're just switching it to look at a different piece of information to populate that switch status from a different place. But from there on in, anything that is using the I/O, the inputs, is looking at process data, I/O switch status, and doesn't know that it's come from a simulated system. And that's a really good thing to have when you are testing, because you can guarantee that once you've tested this input layer and made sure everything works here and is mapped correctly, it can't be something to do with this anymore. It's something to do with your logic. So let's skip back out to the input mapping layer. So you'll notice that I've set these up as arrays. So here I have map generic, 16 of them, array 0 to 15 of my map generic analogs. And if I just make this a little bit bigger, you see I have the same for switch, same for a fixed speed pump, and same for a valve. So I sort of have everything set up for at least 16 of each of these assets. and then I have a specialized one that's sat on its own. And as we go down, you'll see that they follow a very sort of similar theme, which is simulation active. We're checking the simulation status at the top. We process the analog, the inputs, the actual physical input, and then we pass its process data and simulation data. And as we've seen in previous lessons, we pass via in-out, which means that we're only passing the reference. We're not actually copying any of this information. So the thing that's actually updated, where the data is that gets updated, is the global data that we pass to it. So everything is always stored in the global data up here. Is stored in our typed variable list. So QM001 is QM001 here, and the sim data is the same. It comes from a dedicated global variable list which houses all of the simulation data. So you can see here our toggle buttons are done here, the indications are done there, and then we have our dedicated structures which just contain the inputs that we wish to simulate and nothing else. We don't need anything else in these structures. So let's go back to the input mapping, and as I say, the theme continues all the way down. This one here, the quarter turn valve, has got two inputs into it. If we open this one, you'll see that this one has a little bit more going on, and that's because this one is a device as opposed to an instrument. So this one actually has an output as well, something that we pass to our output layer to cause the valve to either open or close. So we have our simulation active here. If the simulation is active, and then our standard pass the simulation information. So if simulation is active, then pass our simulation data IO open feedback into our process data IO open feedback, and the same for the closed data here. But we also have a auto feedback, which is if we're in auto feedback mode, or if auto feedback mode is turned on, then what we do is we update our simulation data. So remember, this is called here to populate our process data. So before we get to this point here, we intercept anything that is coming from our simulation system, and we update it with these values here, which just means that if my process data in my main program is calling for the output to be on, or if a particular mode is set up and we're not calling for something else, it depends what mode my valves are set up in. But let's have a look at this one here. So if auto feedback is on, and I'm calling for the control open output to be on as well somewhere in my code, then at this point here I will update my simulation IO open feedback to be true as well. So at this point here I get my open feedback automatically without me having to interact with my simulation system. And the reason I do that is simply to make things easy for me. Sometimes I might have processes that say, when you start this pump, or if you open this valve, you're expecting feedback within 1 second, and I might have 10 of these open at the same time, which means that I have to be really quick and click open on my simulation system in 10 different places within 1 second, whereas this takes care of that for me. And if I want to turn it off to test fail scenarios where something doesn't open, then I can turn it off and do it manually. So this is a really nice concept, and we'll see this in a little bit more detail when we come into the visualization side of this project, and you can actually see sort of how this works with some actual visual representation. So that's pretty much it for the input mapping layer. To summarize it, it's really just a place where we take our physical inputs, or analog inputs in this case, so AI0, AI1. These are coming from in this project, it's coming from our Modbus layer. So I have a Modbus TCP slave here, and if we just go in and have a look, they're coming from this IO mapping on this Modbus channel. The input mapping layer is simply taking information from that abstraction layer of a Modbus and mapping it to its structures, its dedicated structures, and a nice easy way to have a dedicated layer to bring in inputs and put them in the place they're going to be for the rest of the project.